Okay. Happy Friday, everyone. We're getting close to the end of the semester, as I'm sure you guys know as well as I do. So, we'll spend the first part of the lecture kind of talking about some of the logistics about the end of end of all of this, right? So, all right, lecture 22. Uh, oh no, this is that's from last Tuesday, which we'll get back to that. This is lecture 23. So we're going to talk a little bit about the final exam and self-assessment, a few notes about MATLAB assignments, and then we'll get into 5G and cellular networks in general. So, all right, the final exam, according to what I've uh, found on the final exam schedule should be Thursday, May 9th from 11 to 1. And that will be 25% of your final grade. So, yeah, make sure you put some effort into this. I know you've got capstone and a lot of other things going on, but every course is important. So, occasionally someone ends up with 3 exams on the same day, just the quirks of the schedule, and wants to take mine at another time. And I understand the rules, I understand the concepts there. I just, because of the logistics of teaching this remotely, I've got to jump through a bunch of hoops to make that happen. So please, you need to check your final exam schedules and like this afternoon, and let me know of any issues you might have by Tuesday, April 30th. So do not wait until the last minute. That's not going to make any of us happy. Again, I'm going to accommodate the, whatever issues we have. Just yeah, I hope you understand that it's a lot more complex for me. I can't just have you take it outside my office or something like that, right? So, all right, now before we talk about self-assessment, let's look at the final exam. So I have posted this final exam preview on Moodle on this week's section. And hopefully this will be the third test you've had with me, so you should understand how things work at this point. All right, so I have not written the final exam yet. So some of the stuff is just copied from last year. Will there be 20 questions? Maybe. Not quite sure. But I expect it to be substantially similar to last year's, but we have done things a little bit different this year, right? So most, there are going to be multiple answer, short answer questions. The rest are asking you to sketch something like a constellation or something like that, or to calculate something, right? And I know a lot of our assignments, all of our assignments have been MATLAB based, and you're not going to have MATLAB during the final exam. We didn't do real homework assignments through this, so I'm going to be careful on how I assign you problems. But of course, that's part of the expectation. You just come out of this course knowing how to do some of the basic calculations in communication systems. So, some of this is going way back. This course covers a lot of different materials. So, you're going to want to budget your time. That's why I'm kind of giving you this preview now, to make sure you have a chance to review all this old material. We haven't worked with the Q function in quite a while, but we did, and it'll come back to you, right? So know how to sketch a constellation and the significance, right? So by the final exam, I want you to understand the big concepts and the trade-offs that a practicing communication engineer needs to work with, right? And just like software is a pervasive part of any engineer's life these days, so is communications, right? So we rely on communication so much more than we did a generation ago. So if you go and work for Con Ed, maybe you end up working on a smart grid or telemetry or IoT type application. You're going to need to understand some of the basics about communication systems, right? So want you to understand those, big conclusions that we make, not just, being able to do some little calculation and not even understand what you're doing, right? So as you're studying, make sure that you're kind of like drawing conclusions about how communication systems work and the trade-offs and the constraints that we have to deal with, right? So so that's, just over explaining here the significance of changing M or K in a bandwidth efficient modulation scheme, right? Know how to find decision boundaries, decision errors, and calculate probability of an error for an equal probable binary signaling system, right? So pretty simple one. We've done a binary antipodal one where you had kind of plus and minus one type signaling, or a plus or minus some amplitude A. And we did a unipolar, so it'd be on-off keying 0 and 1 or 0 and A. And we also looked at quadrature, and that would be like 1 and J, or A and JA type of signaling, right? And we've looked at all of those. So you may see another one of those kind of come back to haunt you. So understand the advantage of that raised cosine symbol shape or filter. Again, that's dealing with the inner symbol interference. Be able to calculate a code word. So most of this stuff is more recent, right? So be able to calculate a code word for a linear block code, given an input message and a generator matrix or parity equations. Be able to decode a linear block code using syndromes. Okay, so you noticed if you have turned in your assignment reasonably on time on the block codes, then I've graded those as of what was turned in a couple of days ago, and some of y'all kind of skipped that part about actually taking that syndrome, calculating the syndromes from the parity matrix, and then looking that syndrome up in that syndrome table, and then taking that error vector that is looked up in that syndrome table and XORing that, bitwise XORing that with the results, right? So there might be a little bit of, fraction of a problem there to go through that process. Right? Calculate the path metrics at a certain stage in the trellis given a set of received bits, right? So that Viterbi decoder there, right? And then source coding, Huffman or Lempel Ziv. We did a MATLAB assignment on Huffman. We did not with Lempel Ziv, but it's still pretty straightforward to do. So you should understand how to do that. Understand why and when we might use spread spectrum waveform. Understanding MIMO. Now we just touched on that, right? But we'll talk a tiny bit about it again today. When would it be advantageous to use it? What it requires? It requires kind of a messy channel, right? So you might use a more proper engineering term for that, but it requires a channel with multipath to end up having that diversity of paths that we want to take advantage of with this MIMO type of approach. And then we looked at Alamuti codes, MIMO codes in general. Understand the basics of orthogonal frequency division multiplexing we talked about on Tuesday, why we use it and its advantages, how we can efficiently generate the multiple subcarriers, using a fast Fourier transform, inverse fast Fourier transform, and extract them at the receiver. That subcarriers can be modulated differently depending upon the measured or estimated signal noise ratio in that portion of the channel, and what a cyclic prefix is and why we use it. Know the 5G use cases. Understand basic concepts of cellular communications, dividing the spatial dimension to support. Okay, so we're going to talk about this today. So I probably won't go into this. Understand the standards process. That's going to be the recorded lecture, which yeah, I need to get that done and posted for y'all to look through. So, all right. So, whoops, not that one. Where did it go? Oh, yeah, it's right in front of me. So then, I'm sorry, I never shared my screen, did I? Okay, so sorry about that, but that document is up on the Moodle site. So here's the final exam I gave last year, right? So I may post some of this on Moodle, but here let's just look at a few of these, right? The noise voltage in electric circuit can be modeled as Gaussian random variable with mean equal to 0 and variance equal to 10 to the minus 8. What's the probability that the value of the noise exceeds 5 times 10 to the fifth, right? So that's where you're going to, go back here and look up some of these Q formulas and that type of thing, right? And then punch into this table. Sketch a 16 PSK constellation, sketch a 16 Comm constellation. Both constellations should have an equal distance between nearest neighboring points. Which one has constant? So, like the PSK, yeah, you can. There's some different ways of doing it, right? But you would normally just put those around in a circle, right? And because that circle has a constant radius, definition of a circle, right? Then it's going to have that constant energy all the way around, right? Whereas the 16 Comm, yeah, you'd probably orient that in a square and have some constellation points around in that square, right? So because you're really having this X and Y type of coefficients. Let's see. So yeah, so you might have something, like this, right? So and I'm not going to draw all of them, but note that this one has smaller energy than this one does, right? Your energy is going to be proportional to this vector, right? So, all right. So then, yeah, communication symbol maps system maps 4 bits to a symbol, to a set of symbols, right? So K is 4. How many different symbols are required, assuming memoryless modulation? So that'd be M, that capital M. And then this is that kind of rate calculation. So we've done that. Here's maybe, the probability of error calculation due to additive white Gaussian noise, where you got to use Q function. What advantage does symbol shaped as raised cosine? So, this is right out of the preview, right? So I try not to have any surprises. Determine the code word to send given the input bits and generator matrix. Okay, so here we have the input bits and the generator matrix. And here you need to know, all right, so I'm going to multiply these two together using matrix multiplication, but you got to figure out, does the input bits come first and then the generator matrix, or vice versa, or whatever. Just work through that once. It's trivial, but if you just assume that you know that and wait till the exam, you might be surprised. And that ought to be an easy question, right? So here, this one's a little bit more complex, right? So we're going to need to take a received vector, process it with the priority check matrix. I'll give you the syndrome table. So that's going to produce a syndrome, right? And then you can look up that syndrome, figure out which error vector it corresponds to. Maybe it's 0, right? But most likely it'll be one where you actually do have an error, and then you just XOR that with the R vector. And so circle one of whatever bit was in error, right? And which would be the location corresponding to the one in the error vector, right? And then XOR those to get the most likely. Again, we don't know this for sure. It's just all based upon a maximum likelihood type of thing there, right? So, all right. So, all right, yeah, final exam schedule. If I've done this right, converted time zones, it's 11:45 here, but it's 12:45 there, right? So I think that's Thursday, May 9th from Eastern time, 11 to 1, 10 to 12 my time. So all right, let's see where are we at here. The final exam 24, yeah, so we covered that. Now self-assessment. So it's almost time to start doing that. I'm not going to release it yet. I want you to get almost to the end of the semester. I don't want to load up yet another assignment at the very end of the semester, but this is a chance for you to reflect back upon your understanding of the topic of modern communication systems. So yeah, we should push this as far to the end of the semester as possible, and then look back. It's 20% of your final grade. You can kind of make this a personal statement of your understanding of the communications of the material, right? And it is not an evaluation of the course or of me as your professor. That's, use the regular course evaluations for that. Those should be out and ready for you. And please make sure you do those. But this is different, right? Don't be afraid to give yourself an A, but you need to justify it if your overall grades are lower, right? So now if you've turned in your assignments and you did reasonably well on the exams, you're probably doing pretty well in this course, right? But if you're late or whatever, then yeah, it's your chance to kind of explain some of that, right? So here's what it looks like. It's going to be a Google poll, and it's I'll give you some introductory information here, just for a reminder here that this self-assessment is 20% of your grade. Here's all the learning objectives. Hopefully I've hit these in our lectures and assignments to a degree at least, right? So I mean, it's a lot of different learning objectives to do in one semester of an undergraduate course, but that's what the course description talked about. Now, this cannot be anonymous, right? You've got to put down your name, and because it's part of your grade. I need to know who did this, right? So then here's the big part. Write me a short letter that reflects on your work in this class. Consider the work you did on the MATLAB projects in particular. Did you apply my feedback to improve your work as the semester progressed, right? Did you go beyond just copying my example code that I often present in a lecture? Did you really, kind of put your own work into that? How independently you worked? Obviously some of you all work together, and I said that's cool at the beginning of the semester, but you turn in your own work. How much of that was your own work, right? And kind of be honest with that, because I know. So when you all make the same mistakes, and did you go beyond? Let's see, where am I at here? Did you dig into MATLAB documentation and learn the subtleties of the language and the platform? Did you strive for excellence, or oops, sorry. Here, let's oh well. Did you strive for excellence or just minimally answer the questions? Support your statements with examples and evidence where practical. Did you miss any significant work? Is there anything you're particularly proud of in your work, right? So this is yours, right? You these questions are kind of starting points. Doesn't mean you have to answer each exact question, but I'm giving you a flavor of what I'm hoping to see in this self-assessment, right? Did your exam performance reflect your real understanding? maybe you have test anxiety, right? So this is your chance to explain an abnormally low test grade. So your answers to this question should correlate with the grade you give yourself here in the next question, right? This section can be as short as or as long as you wish, but the more you put in here, the more you can justify your grade chosen in the next section. And here, I'm asking you to give yourself a grade. Now, you should sit back and kind of give yourself an overall grade for the course. When I take this, I'm going to look at what grade you gave yourself, look at what you wrote there, look at your overall performance in a class, and see if that makes sense, right? Hopefully it does. And I will use that, right? And then that will make up 20% of your final grade. So that's it, right? So this is going to require some thought. Start looking at this, right? And start thinking about it. I'm not going to release it yet. And again, these are just kind of example statements, but example questions or things to talk about. But yeah, go ahead and do that. All these questions are required, right? So don't skip this, and make sure you do this. Again, to be clear, this is a required part of your assignments for the course, and it amounts to 20%. The the idea here is that this gives you that chance to step back and reflect. Just like when you study for a final exam, it's you know beneficial to your overall learning, right? If you go back and reflect on particularly your MATLAB assignments and whatever else you did you like look at some of the YouTube things that I posted, like for Turby coding, I think I posted some YouTubes or whatever. I can't remember, but it's your chance to reflect, and I think it's a learning process for you. It's also important for your career, right? You need to be positive, be confident in your career as you move on, but you need to be realistic also, right? So developing these skills to assess yourself in terms of your understanding of a topic is an important kind of soft skill, as we call it, right? So, all right, try to move quickly now. Late MATLAB assignments, they're worth 30% of your grade. You're not going to do well in this course if you've haven't turned in many of these assignments. Most of y'all are very consistent with this and getting things on time. Some of y'all are not. And, there's going to be a little bit of penalties, right? So maybe 1 to 3 points off, or maybe 4 or 5, right? It's my judgment. The assignments were supposed to be turned in on time. I made that clear at the beginning of the semester, but I'm a softie, so I will accept late submissions. But there has to be some accountability to that, right? So if you're still having technical problems with them, right? You're just, maybe you just struggle with procrastination. Maybe you had some crisis in your life. Maybe, you're just not good at multitasking. I don't know what excuse you have. But if the reason why you haven't turned these in are because you're having technical problems with them, you don't know how to solve them, then get with me, right? Make an appointment with me, and let's get through those, right? So the MATLAB assignments are a primary learning tool for you in this class, right? You've got the lectures, you've got the textbook. These last few lectures aren't really out of the textbook. You're not going to find some of this material in there at all. But overall, the textbook has been available to you. But the MATLAB is a very, very important. That's why it's weighted 30% of your grade. It's a very important learning part of this, right? So I want to make sure that you're getting through those. So if you just maybe try to copy and paste some code out of the examples I did in class, and then turn it in and you haven't even gotten it to run or whatever, and it's late, then Yeah, that's it's not going to make either one of us happy, right? So just trying to encourage you to take this seriously. Um, all right, so let's try to get those in by Friday, May 3rd at 5 p.m. Again, they were supposed to be turned in on the date that the assignment is due. And, I hate to make any assignments due at the last day of the regular semester, but really, again, they were due beforehand. So, all right, let's see. Is there anything else I want to show? No, let's go ahead and dive in here. So let's talk about 5G. Now we're 5G is fairly well deployed now, and there's lots of 5G base stations out there, but there's still a lot of these use cases that are still being kind of implemented, and the business aspect is starting to build up around it. But from a consumer level, using that, just our cell phones with better bandwidth and lower latency, yeah, that's a lot of base stations out there these days, right? So, and we're starting to work on 6G. So, uh, 5G is designed to operate in the traditional cellular bands, and we denote that as frequency range 1, FR1. And those are generally between 450 megahertz and 6 gigahertz. That the exact allocations are, dependent upon each country's regulatory environments and what carrier bid for what chunk of spectrum and that type of thing. But then there's new to 5G is the millimeter wave bands way up at 24.25 gigahertz to 52.6 gigahertz. Dramatically different frequency range, and a lot of different engineering issues apply to FR1 than they do to FR2. Right. So in particular, the low bands are dominated by concerns about spectral efficiency. We really don't have enough spectrum available to us in this low band. And so, the standards as they've evolved from 2G, 3G, 4G, and 5G, and next 6G has been focused on trying to maximize that capacity per bandwidth, right? C divided by B. And but the high bands are dominated by coverage challenges, right? Up here at this crazy high frequency, due to the higher propagation losses that you experience and difficulties in achieving high RF power efficiently at the current state of the art, right? So back when I started my career, 6 gigahertz was super expensive and hard to produce. You might have been using vacuum tube type technologies at microwave frequencies, and but now we've got transistor technologies, even an integrated circuit that can produce reasonable power at these frequencies. But maybe someday this frequency range gets easy, but right now it's really hard, right? So SOTA is state of the art. Some aspects of 5G are shared between the bands, while others are more relevant to a specific band, right? So we have one standard, and we try to share as much of that between these two bands, but there are some specifics for each band, mainly because of these trade-offs, right? So let's talk about 5G NR, new radio. It's crazy that they name something new because eventually it's not new anymore, right? But it's called 5G NR. 5G uses OFDM on both the uplink and downlink, right? So the uplink would be your cell phone talking to or transmitting to the base station, right? And the base station's in receive mode, you're in transmit mode. The downlink is the opposite. The base station is transmitting and your cell phone is receiving, right? So you can kind of think of relative antenna heights, right? So normally the base station is much higher And so when it's transmitting down, right? It's downlinking. And when you're transmitting, you're kind of transmitting uplink. So it uses OFDM on both the uplink and the downlink. They're slightly different in the way they're standardized and formed up, but 4G uses OFDM on the downlink, but then this thing called single carrier frequency division multiple access, SC-FDMA, which has some similarities to OFDM. You do use some Fourier transforms, fast Fourier transforms in it, but they're much smaller in size, right? So instead of maybe a 1024 point FFT, it might be a 256 point or 128 point FFT or something, right? So it's easier on a power amplifier, this FDMA thing, but requires supporting yet another waveform. So 5G, we're tackling this power amplifier efficiencies issue. We've kind of improved our technologies in that area, so we can use OFDM on both the uplink and the downlink. So OFDM symbols are arranged in a resource grid in both time and frequency as slots. Okay, and now I've got some numerology here. So actually, let's see if I've got okay, so here's a standard. Let's see. So this is showing a little bit about the OFDM waveform, right? And so your channel bandwidth would be at this wide, and the we fill these transmission these resource blocks, and also on this higher frequency side, we don't transmit a block at the very center of it. That corresponds to DC, and there's just some issues in implementing that. And so we normally set that the subcarrier that's right in the center to 0. And then we also have these guard bands that are set to 0, so that even this is idealized, right? So here's more of our realistic spectrum shape that we might have, and we just want to make sure that it doesn't bleed over into the next channel beside us, kind of like you see here. So let's see, is there a resource block in this one describing it? No, I guess not. Okay, well, I'll show you some more standards on the recorded lecture, and so we'll see some of that information there. But you remember from the lecture we had last week, or I'm sorry, on Tuesday, that we had this kind of block here, right? So this is kind of generic, but ultimately this is going to be an OFDM symbol here, another one, another one, another one. All this is going to be gathered up in a frame, right? So we got the subcarriers along here and the symbols along here. And we'll have a certain number of symbols in a frame, and then we send that frame. And then we actually kind of have some subframes associated with that also, right? So maybe there's a certain number of symbols in a subframe, and then a certain number in the total frame, right? So so in this case, we've got these symbols arranged as slots, and 14 or 12 OFDM symbols, right? So there's some flexibility in the standard depending upon your use case and the actual implementation. So you might use 14 or you might use 12. You can't just decide to use 13, right? We've got to have these things standardized so that our different radios know how to communicate with each other, right? And then these are organized into subframes, right? So this is going to be a little bit of a function of these slots here, the number of DM symbols, but basically there's like subframes at 1 millisecond. There'd be 10 of them, and a total frame would be 10 milliseconds, right? And inside certain specific locations in this frame are going to be things like pilot tones or reference signals and synchronization symbols, and these things that are exchanged between the base station and the subscriber unit to know, all right, which slots is the base station expecting the radio, the subscriber unit or user equipment to be transmitting in, or which ones are which part of that slot or that resource grid is destined for me, right? And what kind of MIMO mode is being used right now? How much power should you use to transmit? And all sorts of different control information. That's all in well-defined parts of these frames, right? So that's why we have things organized in frames. And then you would send a frame, and then all that stuff would be have error control coding associated with it. And so if you're not able to receive some things, then you're going to exchange some control information in some of these, right? All right, then we talked about these subcarriers. So they are spaced in a flexible way, but still standardized. It could be 15 kilohertz. And again, each of those would be modulated using some version of BPSK, QPSK, 16 QAM, 64 QAM, 256 QAM. There may be some higher ones supported under certain conditions if you have really, really great signal noise ratio. And so each one can have a certain modulation. Usually it's assigned in these resource groups, right? But that subcarrier now is going to have, if it's 16 QAM, that's M equals 16. So K would be 4, right? So if K is 4, it's going to take 4 bits and then modulate that using 16 QAM. It's going to produce a certain symbol, and that symbol is going to be in that subcarrier, right? And so it's going to be transmitted in this 15 kilohertz bandwidth. So then, or you could have wider bandwidths, and the wider bandwidths could support faster data rates or shorter symbol durations, right? So if you have a nice long symbol duration, then you can use a smaller bandwidth. If you have a shorter symbol duration, that means you're sending symbols at a faster rate. You're going to need wider bandwidth, right? So your maximum system bandwidths overall, 50, 100, 200, 400 megahertz. These are crazy wide bandwidths compared to previous generation systems. So there's different versions of the cyclic prefix, and some odd numbers there, but maybe I missed a decimal point on that 12 right there. Might be 1.2. I'd have to double check that. But your maximum FFT size is 4096, of which 3,300 would be used, and the rest would be set to 0, including that DC carrier, and then the guard subcarriers at the edges of the spectrum. Right. So, and all right. So, I'm not expecting you to memorize these numbers any more than you would. I expect you to memorize every single formula used in class and stuff, right? So, if you work with this, you start looking up in the standard to implement it, and eventually maybe you get to know them. But yeah, they're available, right? Um, uh, but you should understand the concepts that these are flexibly set based upon implementation, and some of these are dynamically, very dynamically set, right? Um, but yeah, the rest would probably be much more static. You might decide to use this for a particular use case and stuff, and set up your base station and your user equipment, subscriber units accordingly. All right, so we have these resource blocks. There's 12 consecutive subcarriers in a frequency domain, right? So again, we don't try to specify this modulation depth or symbol duration or whatever for each single subcarrier. We're going to do that at the level of resource blocks, right? So 12 consecutive subcarriers in a frequency domain. And these can be scheduled to individual subscriber units. So I can say, well, resource blocks 1, 2, and 3 are to this user, and resource blocks 4 is to another user, and so on, right? And the base station controls that. There's these primary and secondary synchronization symbols. So these would be codes with good autocorrelation and cross-correlation type of parameters, and these are used to help the receiver synchronize to the transmitter in time. There's some information carried in this, like it'll have a cell ID in there, but so that allows just at a very low kind of hardware level the receiver to synchronize to the transmitter by doing an autocorrelation or cross correlation with these synchronization symbols. And then there's these other reference symbols that I've mentioned, these pilot tones or reference symbols scattered throughout that resource grid. And they're, again, known values of modulation, and they help the receiver equalize. All right, so then there's these MIMO modes. So we have in the low bands, extend and enhance the MIMO technologies used in previous generations. 3.5G and 4G is did have a lot of MIMO type of things, and so there are different modes of MIMO, and we've touched on a few of those, and we looked at Alamudi the other I think that was last Friday. And so that is one of these orthogonal space-time block codes. So here's another example of it. Here we send we have these symbols S1 and S2, so we're sending a pair of symbols at a time, and we send them twice, right? And we send S1 on the first antenna and S2 on the second antenna. In the second period, we send minus S2 complex conjugate on the first one, and I think that's supposed to be S1 on the second one, right? So, and then you multiply by this matrix, and yeah, you end up with your estimated values received in a matrix. Here, the key is you're sending two symbols over two periods, and you're getting a better response out of it, right? So here our noise is multiplied by our H tilde here, but our symbols are multiplied by this norm squared of the of that. So there's a gain, as we would hope, right? All right, then here's the main difference. In the high bands, we emphasize beamforming techniques to overcome propagation loss challenges. So we form beams that align with propagation arrays while possibly forming nulls towards interference sources, right? So here we might have some I don't want a laser pointer. I want to draw. Okay, so we might have these different antennas, and then they're set with certain phases, and so they would combine to concentrate the beam in this direction, right? So let me show you. Oops. I'll keep those for now. And okay, here it is. So this is a bit of an older article written by Thomas Cameron. I worked with him in the at competing companies, but back in the late '80s, early '90s, I worked with Tom, and so now he's working for Analog Devices, or he was back in, I think this is a 2017 article. So here we see that there's these different antenna elements, and they might be encoded into a very small antenna. Again, at 20 some odd or 30 gigahertz, your wavelength is really, really small, right? So your antenna array element spacings are typically on the order of a half wavelength, right? And so here they've arranged them in a square, rectangle. And so we drive each one of these with a specific amplitude and a specific phase, right? And in this implementation, we've go through a digital to analog converter. So we've got an analog, an RF signal here. We up convert it to the gigahertz, the 10s, 20, 30, 40, 50 gigahertz range. And then we're tweaking the amplitude and the phase of this and then amplifying it. And so there's one of these chains for each one of these antenna elements. And by adjusting that, then we can have a beam in this direction. And actually, we can have multiple beams, right? So we can have a beam in this direction, one in this direction, one in this direction, and so on, right? So that way we can support multiple different users, but we're concentrating our beams in those directions, right? And then we have kind of the dual of that. Well, okay, so here we not a dual. These are M different antenna groups, right? So so that's the kind of concept of this. So there's lots of different ways of implementing this, right? And these controlling amplitude and phase at these millimeter wave frequencies is very difficult. Some of this technology came about in big phased array antennas that are like ship scale on Navy ships, like a cruiser, a Navy cruiser, and using a big phased array antenna. Or there's antenna arrays that are size of buildings that the Missile Defense Agency uses to try to scan for any incoming ballistic missiles and to track them. So that this technology is being developed since the 70s and 80s, but very expensive. The idea of now trying to miniaturize those onto a microwave integrated circuit is very, very challenging, right? So another way of doing it is to have multiple DACs here, and so one whole signal chain for each antenna group here, right? All right. So we can form beams that align with propagation arrays or directions, right? So we want to form beams towards individual users out there. And if you have enough degrees of freedom and enough processing power and sensing power, then you can possibly form some nulls towards interfering sources, right? So if there's someone interfering with you, then you can create a null in your antenna pattern to be able to do that, right? So there's lots of research in this area of how to calculate that, how to estimate that, maybe using some machine learning type of approaches. So what, sounds great, but what are the challenges, right? So you must estimate where the subscriber units are or where the interference is, right? So you've got to know if you want to really do all of it, you've got to know where those are, right? And then in a lot of cases they don't stay put, right? So they move. Now maybe we're a long ways from us as consumers using these high bands in our cell phones that we use, right? So this upper band or this high band is, maybe suited for some of these other type of use cases, maybe that ultra reliability, low latency type thing, where you might be doing some remote surgery or autonomous vehicles or that type of thing, right? So maybe in that remote surgery, you're not moving. There's not a big mobility thing, but in general, you've got to deal with this time varying aspect, and it's non-trivial to do this over a wide bandwidth, right? So why do we want these high bands? Well, because bandwidth is easier to come by from an allocation standpoint, and it's hard to find a spare 100 megahertz or even a gigahertz at these low frequencies, right? 100 megahertz and around 1 gigahertz. That's a lot of bandwidth, relatively speaking, right? But when you're up at 20 gigahertz or 30 gigahertz or 40 gigahertz, 100 megahertz is nothing, right? So we want to use these modes where we need this super wide bandwidth and for that use case. But doing this beam forming is hard over these wide bandwidths, right? So I know this is an antenna course, and antenna theory is for arrays is kind of a graduate level thing, but you form these beams by adjusting the phase of the signal going to each one of these, right? And they're again spaced on the order of a half wavelength, between each antenna element, and you're tuning these with a particular phase to steer this, right? You might be steering it off in this direction, or down in this direction, or straight ahead, or something like that, right? So you're doing that by adjusting phase, but phase is sensitive to the frequency that you're operating at, and that's hard to do over wide bandwidth. You could adjust delay, and then that's a wider bandwidth type of approach. I've done some work on that, but that's a fairly expensive type of thing, especially to do with the type of resolutions that you can get away with in phase. All right, so the point is that it's challenging to do that beam steering over a wide bandwidth. And all right, so we use channel coding, and we looked at linear block codes. We looked at a Hamming code in particular. We've looked at some convolutional codes in 5G, 4G, 5G, 6G. We're using more complicated codes than that, and one is a family of codes called these low density parity check codes, and then also polar codes. And for the sake of time, we're not going to go into these, but just know that, yeah, they owe their existence back to some of these codes, more simple codes that we looked at. And a lot of times in these communication systems that we'll use a combination of codes. We might use linear block codes in combination with convolutional codes at the same time. But these are a little bit different type of technology. All right, so now let's spend the rest of the lecture talking a little bit about kind of the system level, the cellular system level concepts. What do we even mean by cellular communication concepts? Well, in the 70s and before, if you wanted a phone in your car as you would drive around, there would be basically one big antenna in the middle of your city. Maybe it's on a very tall building, or maybe it's in a mountain that's right next door, or something like that. You get as high as possible, you transmit as much power as you can, and basically you have one cell. And so there's only a tiny number of users that could be talking on their car phones in any given area, metropolitan area. There might be 10 megahertz allocated to that, and voice communications only takes maybe 20 or 50 kilohertz. So you could have some number of users allocated, but then that's it, and you can't get any more. In those days, you would devote much of your trunk in your car to the radio equipment, but so there was just a scalability problem, right? You can not support kind of infinite number of users, only a few users, right? So what cellular communications does is it divides up the spatial dimension, right? So we've talked about how we can divide up time, and we can divide up frequency. We can use some spreading codes like CDMA to support multiple users in a certain area. What cellular communications does is that now it adds yet another kind of dimension to all of that, and that's the spatial dimension. So we're going to divide up things. We're going to use much smaller cells with much lower power radios than was done way back when. And now we only transmit over maybe a few miles, right, or a mile or two, type of thing, right? Depends on whether you're building a cell station in an urban city like New York, where there's a lot of users, and so you need very small cells to be able to support lots of different users over that metro area. Or you're let's say upstate in the Catskills or something, and then hardly, your user density is far lower, so you would have bigger cells covering a larger area. But the idea is that we're using many lower power radios arranged in cells. The cell size, smaller supports more users, but then you need more cells to cover a certain geographic area, right? So the more users you have, then kind of the smaller you design those cells, because each cell is, even though we've come a long ways in enhancing spectral efficiency, they're still only going to be able to support so many users in a particular cell. And so if you have lots of users, you need to go to smaller and smaller cell sizes. That means you need more cells overall, right? And that's going to result in a higher, what we call CapEx. That stands for capital expenditures. So two acronyms that are super important in wireless communications, and cellular communications in particular, are CapEx, is capital expenditures. That's the cost of your building your towers, the base station equipments, the antennas, the fiber optics to connect all the base stations together and that type of thing, right? So those are capital expenditures. You got to buy things and send people out, teams out to install these things, right? And then you have OPEX, operational expenditures, and that's would be more like your electric bill to run these things. Maybe you don't own a tower, and instead you rent space from them, from a tower owner. That's actually typically a case. These carriers don't own their own towers anymore. They're owned by, in the United States, are owned mostly by American Tower or Crown Comm, I think, is the name of the company. So then these cells are further divided up into sectors. So most towers use 3 sectors each, spanning 120 degrees. So if you look up at a tower, most of the time you will see 3 sets of antennas facing outwards, and they're each spaced at 120 degrees around the radius of that, or around the circumference of that tower. And so they're transmitting and receiving in this sector. So now we've divided these cells up even more, right? And now we have this frequency reuse pattern minimizes intercell interference. Okay, so we have this small cell size, but then we have got a cell next to it, right? And if they're operating at the same frequency, then there's a possibility or probability that at kind of the boundary where one cell kind of stops and another one starts, you're going to have some interference from the other towers, right? And RF signals just kind of fade away. They don't just drop off, right? So at a certain distance away from the antenna. So we've got to deal with this. Now, OFDM, and we'll add an A onto that. OFDM-A, multiple access, will take that resource block that we might be transmitting and maybe allocate a certain part to one tower and a base station or cell, and another part of that to another tower or cell. But in general, we have this idea of this frequency reuse. So here we might have a cell here, and so the cells are actually, the tower is actually located at these vertices. And do I have, let me actually just use this color here so the red doesn't blend into the red background. So your antenna tower would be here, and it'd be transmitting in this sector using frequency 2, transmitting in this sector using frequency 7, transmitting in this direction using frequency 1, and then you'd have a tower over here, and so on, right? So it's designed to not have these interferences. So each tower in each sector is using a discrete its own set of frequencies to assure that we're not interfering with each other, right? So note here that these antenna patterns are not really these nice hexagonal things. They just fit together, right? In this way, using a 3-sector type of approach. And so the idea here is that you can have 7 different frequencies, and you can see that this cell is not going to have any, or let's work over here, right? So this cell is not going to have any frequencies that are similar to each, that are the same as it, right? Adjacent to it. So if this cell is transmitting F2, then it's in this hexagonal type of pattern. Then you've got 6 sides adjacent to it, and they're using those other frequencies, right? And then you step away, and you see that there's again, for this cell, you're having a different set of frequencies. So That's the idea. There's a whole profession of cell engineer optimization person, and that will actually look at the particular area and figure out what is the coverage from this cell. And it's, like I say, it's not really hexagonal. It might be more kind of circular, or in a sector it would maybe have some kind of main lobe shape, but it's affected by buildings and terrain and that type of thing, right? So um, and so again, these things aren't quite so pretty and uniform in real life, but this is kind of the abstract way of looking at it. So here the key is you've got these cells that are transmitting in three directions, and so you've got kind of a hexagonal type of format to it, and you can use this frequency reuse of 7. So if you're a carrier and you've bought some spectrum in this particular area, then you take that spectrum and you divide it up into 7 different channels, and then you operate each base station at one of those frequencies. All right, then here's some other important concepts. Then we have this idea of handoff, right? So this maintains subscriber units to connections to the best tower and sector combination, right? So as you move, as you're driving down the highway or you're riding on a subway or something, then you're going to ultimately, if you travel far enough, you're going to move from one cell to another, one sector to another. It might just be the same tower, but a different sector of that tower, right? And so this concept goes back to kind of the early days of cellular communications. And again, OFDM the orthogonal frequency division multiple access, gives you some more flexibilities, but the basic concepts here are that we would have a hard handoff where we would cleanly switch from one tower sector to another, right? So at some instance of time, the base station decides, okay, you're really too weak for me to communicate with you, but there's another tower, another sector that's good, and so I'm going to hand you off now, right? And it coordinates this with the base station at the other tower, right? So there's some computations going on at a little bit higher level than the towers are, and it's deciding, it's tracking the users and their RF performance that they're presently achieving, and trying to decide when to switch them to a different cell that is better able to handle them. And in this hard case, it is talking 100% to one base station, and then at a certain time, it stops talking to that base station, starts talking to another base station. It's at that 100% either or, 0 or 100% type of level. A soft handoff now maintains multiple connections in the transition area, and this is a big deal in CDMA type technologies. And so in that case, and some and some more modern systems also, is you can allow that user to talk to 2 base stations at the same time, and then the signals can still be combined to actually kind of even enhance the signal, right? So then there's the idea that the base station or higher, the base station controller and higher handles this handoff while communicating with the other base station controllers. So the user doesn't decide, oh, I'm going to start talking to another one. The user equipment doesn't do that. It's the base station that's coordinating or orchestrating all of that. All right, now we have these towers, but they ultimately have to be connected to each other, to other computers that are controlling the overall cellular network for the carrier, and then ultimately it needs to be connected to the regular telephone network, and which hardly any of us use anymore, but the old landlines type of thing, and also the internet, which is actually where we spend most of our time these days, right? But that cellular system needs to be connected to this, and that's physically moves from the base station tower over, most of the time it's going to be over fiber, right? So now you're aggregating all the users in that particular area, and you're putting it onto fiber and sending it back to a network switch that the carrier operates, and maybe they operate a few around the country, and these are ginormous rooms with tons of computing processing power and all. So or in very remote locations, if you're want to put a tower up on a mountain up in the Adirondacks, well, you're probably going to use a wireless link as your backhaul, right? And then we have this idea of this radio access network, and this has gotten more complex in 5G and 6G. So we have this idea of a split RAN. So they radio access network's going to include the power amplifiers and low noise amplifiers and all that RF equipment, but also all that baseband modulation of taking those bits and forming them up into symbols and OFDM symbols and whatnot, right? And then all the other signaling that's going on. And so you might have a radio unit that might be on a tower itself. In the old days, it would be at a small building at the base of a tower, or a cabinet at the base of a tower, and then it would run coax or up to the antennas. But now more and more we're putting the radio, the RF units up on the tower, and then fiber optics down the tower to the cabinet at the base. So we have this distributed unit, the idea that you've got something at the base of a tower, and then you can have a centralized unit, and you can have that at an edge server location, which you might have in one community type of thing. So yeah, there's a lot of acronyms here that we're not going to cover. I try to explain a few of these, but the idea here is that you've got different stages from this radio resource controller all the way to the RF and the antenna, and then from the antenna all the way back down to here, right? And we've got data at this point, raw data, right? And all this other stuff is forming up those symbols and that type of thing. And the idea here is that we can put some of this at the tower, and some of this at the base station, and some of this in a centralized edge server location, right? So, for example, the Open RAN Alliance pushes for a 7.2 split RAN, and that's an example here where this would be the radio unit. You're doing your FFTs and your E to Ds, D to As, and all your amplification and up conversion, that type of thing. And then you've got your media access controlling, some of your MIMO processing, and radio link controlling here. And that would be in your DU, which would probably be at the base of your tower. And then you would have these higher things, right? So NVIDIA implements the 7.2 split with their aerial system, which includes their famous GPUs, right? So they're not just used for graphics rendering and machine learning, they're used in communications also. And they've got a CU-BB framework and a CU virtualized network function, VNF. And that everything's very time sensitive, so it uses this time triggered networking. All right, perfect timing. Have a great weekend. Use this to get caught up, start studying, all of that. Thank you.
What was it?